All right, it's 2:40. We should get started. Looks like we still have a few people coming in, but we'll just start with the announcements. Let's see. Next up is exam 2, and I'll release that on Friday. I've talked about it before. Just this is stuff that you should know by now. I'll release it on Friday at noon. I haven't written it yet. I'll write it tomorrow. And it will be due Saturday at noon. And I'll also send out an email reminding everyone so they don't miss it. I do drop one exam automatically or half of the final. The final counts as 2 exams. So some people choose not to take the second exam, but it's usually not the best strategy. If you did really well in the first exam, I can understand the temptation, but this material is going to be on the final exam as well very soon, only a few weeks away, because the final is cumulative. So and you don't know how the final will go. Yeah, maybe the final is the one where you want to take the pass at least on half of it, the drop on half of it. So I do recommend that you take the second exam and don't just rest on your laurels from the first exam. Any questions about the exam before I move on to other stuff? Okay. Homework 7. I know it's the last thing you're thinking about because the exam's coming up, but it is going to be due a week from tomorrow. So on Thursday, which is unusual for us, as I described last time, homework 7 will be due on Thursday, homework 8 the following Wednesday, homework 9 the following Tuesday, which is the last day of class. Picking up the pace for these last 3 units. They're a little bit shorter, and so it should work out just fine. Just be aware, and we are on pace. We won't be extending that one. It will be due on that Thursday. Oh, and with the exam, just to reiterate again, it's just on lessons 4, 5, and 6. So telescopes, the overview of the solar system in lesson 5, and the moon and Mars in lesson 6. Sorry, Earth and the moon in lesson 6. Mercury that we did last time, Venus, which we'll do this time. My brain is frazzled. Mars next time. None of that will be on the exam. So just up through the moon. Trying to think if there's anything else. After we're done with the second exam, we'll pick a date for the final. As I talked about, since we're giving it online, we don't have to do it at the regularly scheduled time. I got permission from my department chair for both sections to take it simultaneously, again, over a 24-hour period. We just have to pick the date, and I'll survey you all either on Monday or Wednesday to figure out what date works best for you. Warm-ups, I've posted the warm-ups from lessons 4, 5, and 6, the ones we did in class, plus a few that we didn't have time for. They've been posted since Monday evening, and so you can use those to study from as well. And I think that's it for announcements. Does anyone have any questions about anything? Okay, well, let's take a look at today's warm-up question. And this is also tied to lesson 6. So this is the kind of thing you can expect on the exam, radiometric dating. Here we're looking at a zircon crystal extracted from a meteorite. So something came in from space, landed on the Earth, and we dug into it and pulled out a zircon crystal. In this crystal, we find 1 uranium-235 atom for every 63 lead-207 atoms. And this decay from uranium-235 to lead-207 has a half-life of 0.713 billion years. So how old is this meteorite in billions of years? Okay, we got 9 submissions. I'll give you all a minute or so. Do give it a try, because there will be something like this on the exam for sure. Another 20 seconds. Okay, let's see how we're doing. We got a few more. This looks reasonable. Yeah, so most of you got the right answer, 4.3. Some of you are a little bit high or a little bit low. Let's walk through it. So kind of the key thing here is the zircon. Now let me put this back up. Key thing here is the zircon crystal, because as we talked about last time, there are many, many ways to make different isotopes of lead. Just because you see lead-207 in there doesn't mean it necessarily came from the decay of uranium, except if it's in a zircon crystal, there's no way for lead to become part of the lattice structure as those crystals are forming. So any lead that you find in there did come from the decay of uranium. Okay. There are other ways to do radiometric dating where we can guarantee that in this case, lead came from the original product. This is just a common example using zircon crystals, and it's the one we focused on last time. So let's work through this. If we have, let's see, the number of 235 uranium now, that's 1. And the number of 235 uranium originally is that 1 plus those 63 atoms of lead-207, because since they're in the zircon crystal, they had to come from uranium-235. So originally we had 64 of these. And so the fraction, it's still uranium-235 is 1 out of 64, which is 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2. 2, 4, 8, 16, 32, 64. So that's 1/2 raised to the 6th power. That means we've been through 6 half-lives. 6 times 0.713, and that's billions of years. That's giga years. Giga means billions. So 6 times 0.713 is about 4.3 gigayears, which is just a little bit younger than the age of the solar system. So this thing formed shortly after the solar system did. Okay, y'all see how to do that? Cool. Okay, so on to today's topic. Last time we finished up with Mercury, water in the polar regions of Mercury, frozen in the craters. Now we're on to Venus. No, not that Venus, this Venus. So back to the dot cam. Venus. And here we see, kind of a standard image of Venus. It's completely enshrouded in clouds. Makes it a little bit mysterious. We can't just see what's going on the surface. We figured it out, but it's taken a little bit of work. Here it is compared to Mercury and the Earth and Mars. And I've filled it in a little bit so you can see its full extent. By the way, this is a gibbous Venus. And as we learned back in lesson 2, the gibbous Venus is evidence for the heliocentric model. In the geocentric model, you can never have a gibbous Venus. And here's one nicely imaged, just an aside. But anyway, looking at these, it looks very similar, at least in size, to Earth, and very different in size from Mercury and Mars. We often think of Mars as our future destination for humanity, and there are good reasons for that. But initially, just from the sizes of the worlds, Mars seems a piddly little planet like Mercury, and Venus seems more like Earth, again, just in terms of the size and also in terms of the mass contained. So let's take a look at our table here that we had last time with the different terrestrial planets. We went through Mercury last time. Here's Venus, and here's Earth underneath it. And the first column is radius, and Venus is about 95% the radius of Earth, so a little bit smaller, but comparable. The mass is 82%. So again, a little bit smaller, but still comparable, especially compared to Mercury, which is 5.5%, and Mars, which is 11%. Then we can calculate our three favorite things that we can calculate from mass and radius. And that is average density, surface gravity, and escape speed. Again, average density is mass divided by radius cubed. So if you take this number and divide by the cube of that number, you'll get Venus's average density as a fraction of Earth's. Here we've multiplied it by Earth's average density to get Venus's average density, and it came up to be pretty much the same, which means that Venus's composition is probably similar to Earth's. Similar fraction of metals versus rocks, probably a similar interior structure, as we'll see. Again, Mercury also has a similar density, but it's misleading because there's so little mass there. It's not being compressed like it is here. So comparing Mercury to the Earth is like an apples to oranges comparison, but comparing Venus to the Earth is like an apples to apples comparison. Similar amounts of mass, similar amounts of gravitational compression. So we can legitimately compare these two numbers and say, yeah, Venus is very similar to the Earth in terms of its composition. Then we have surface gravity. That's mass over radius squared, and it comes out to be about 91%. So if you went to Venus, your weight would be 91% your weight here. So very similar. And then the escape speed, square root of mass over radius, gives you the escape speed as a fraction of Earth's. Here we've multiplied by Earth's escape speed of 11.2 kilometers per second and got Venus's. And again, very similar. And none of this is surprising. It has about the same radius, about the same mass. So these three quantities should also be about the same. In its bulk characteristics, it's very Earth-like. But as we'll see, there are some significant differences as well. Let's think about its orbital properties. And it is an interior planet closer to the sun than us, which if you think back to lesson 2, when we were building our models of the solar system, that means that it will always be within a certain angle of the sun. Now, Mercury is very close to the sun. Venus is much closer to us. So it's a bigger angle. It's about 47 degrees at greatest elongation. So it can either be trailing the sun in the sky, in which case the sun sets and then Venus is up in the evening sky, and we call that the evening star. Or it's ahead of the sun, in which case it rises first, and then the sun rises. And during that period of twilight before the sun rises, we call that the morning star. Of course, it's not a star, it's a planet, but Venus is very, very bright because of its close proximity and also its great reflectivity, as we'll see. And it has the kind of the common name morning star, evening star, but again, it's not a star. Here's Mercury's orbit for comparison. And again, Mercury is a little bit eccentric. Its greatest elongation can be between 18 and 28. Venus's orbit's much more circular, it's farther out. And so you have this longer period of time to observe it before it sets or before the sun rises and ruins it. And we looked at this picture before in a different context, but here you have the sun setting somewhere over here. This is right at sunset. And here you have Venus pretty close to greatest elongation. The moon happens to be next to it, which is irrelevant for the concept, but pretty to look at. And it would be about 3 hours. When at greatest elongation, you have about 3 hours before Venus will set. Or if it's on the other side, Venus rises and you have 3 hours to observe it before the sun comes up. So a much greater window than we had with Mercury. And so we can get much more information about it. such as these pictures here. These are just pictures of of Venus's cloud structure, and Venus is completely covered in clouds. So that's the first difference with Earth. With the mass, the size, all very similar to Earth. We're partially covered in clouds, but Venus is completely covered. These are taken in the ultraviolet, which is useful for bringing out some contrast. And this arrow has just been drawn on where there's a little nook in the cloud structure here. And so you can track it as the planet moves, well, as the clouds move anyway, and you can determine how fast those clouds are moving. And the clouds on Venus travel about in the upper layers that we're looking at, about 300 to 400 kilometers per hour, which is not very dissimilar from how fast the clouds move in our upper layers, or how fast the atmosphere moves in our upper layers. So even though it's completely cloud covered, the wind speeds in the upper layers seem kind of similar to Earth as well. So people just kind of thought, well, beneath those clouds, there's a planet that's probably rotating once a day, because everything else seems like Earth. Probably that's going to be the case as well. But we can't tell because we can't see it. All we see are these clouds. There's never a break in the clouds for us to see surface features and track them. So we used the same trick that we use with Mercury. We shine radio waves up against the planet and use the Doppler effect. The radio waves go completely through the clouds as if they're not there. So we send out one wavelength and it bounces off the surface. It bounces in the middle. It comes back the same wavelength that we emitted. But if it bounces, well, for those wavelengths that bounce off of the side that's approaching us, comes back blue shifted, and the side that's receding comes back red shifted. So we send out one wavelength and we get a range back. And from that range, we can determine how fast Venus is spinning on its axis. And we were all quite surprised to learn it rotates, so it spins with a period of, I have it here, there it is, 243 days. Very, very slow. Off the top of my head, I don't know of anything else in the solar system spinning this slowly. So certainly not once a day. And if we were thinking about going to Venus, we would have to get used to a much longer day-night cycle. So this is our first big stumbling block for Venus being a future Earth. And we'll see there's some other pretty significant ones, which is why we've instead focused on Mars despite its much smaller size and weight, size and mass. The orbit, the amount of time it takes to orbit the sun, is 225 days. So it takes longer to spin on its axis than it does to orbit the sun. And the spin is backwards. Most things orbit and rotate counterclockwise as viewed from the top, as we learned before. Venus is spinning clockwise. It's still orbiting counterclockwise, but it's spinning clockwise. And so here you can see the arrows reversed. It's a backwards rotation. So what would cause this super slow backwards rotation? Well, no one knows for sure, and there are kind of three plausible theories. And we really can't distinguish between them with the data that we have. I'll just mention all three. The first one is something big hit it. On the side, if it was spinning this way, something came in and nulled out its rotation, maybe reversed it a little bit. And this seems kind of extreme, but we've already seen a major collision with Earth, possibly a major collision with Mercury. We'll see a major collision with Mars, and other evidence for major collisions, like planet-to-planet collisions in the solar system. So given all that, this is not too crazy an idea. If it came in and just hit it on the side, nulling out its rotation, that could do it. Now, originally, there were probably twice as many planets as we have today. They gravitationally settled where they are, and part of that settling process was near misses, and some of that settling process was collisions. Second possibility is its atmosphere slowed it down, just the winds. There's friction between the wind speed and the winds, given their high speed, and the surface. It may seem kind of crazy that winds could stop the rotation of a planet, but it's had 4.5 billion years, 4.6 billion years to work. So there have been some studies that suggest that just the winds could have done this. It has a thick atmosphere. And third possibility is that Venus was closer to the sun in the past and got tidally locked. Gravity drops off as 1 over distance squared. Tidal forces, it's 1 over distance cubed, I think. It may be 1 over distance to the 4th power. I can't remember. It's one or the other, but it drops off faster. So once you get far enough away, tidal forces don't matter. You don't get tidally locked. The only planet that is dominated by tidal forces is Mercury. Most moons are close enough to their planets to be tidally locked. Venus is just a little bit outside that range, but we'll learn that the planets, their orbits shift. Sometimes they're closer, sometimes they're farther away. Part of that is just clearing out the early solar system. There's so much stuff, debris, other wannabe planets, that as some planets chuck these out, they recoil and change their position. Also, the planets are always tugging on each other. So over long periods of time, they can get closer to and farther from the sun. And if, we don't know, but if Venus was a bit closer to the sun, it could have gotten tidally locked, and that could have nulled out its rotation, and then it moved farther away, and they've become unlocked, and it's picked up a little bit of a difference. But these two numbers are pretty similar, so it's suggestive. Again, we don't know. It could be any of these. It could be a combination of these. And this is how it would work out, because remember, it's orbiting counterclockwise, but spinning, rotating clockwise. And so if it's noon on Venus, and you're standing here, the sun's overhead, the sun would set 39 Earth days later, would rise at day 78, and be noon again at day 117. So although it takes 243 days to spin on its axis, the day-night cycle would be shorter because halfway through that rotation, it's carried to the other side of the orbit, shortening the day-night cycle. But still, 117 days is a pretty long period of time. If we were to colonize Venus, biologically, that would be very difficult to adapt to. Staying up half that time, sleeping half that, no, we'd just have to get used to it being daylight for long periods of time and dark for long periods, like scientists at the South Pole. But there are other more serious problems for colonizing Venus. Let's move on to the interior. And this will go pretty quick because we don't know that much. All that we know is that average density. And so we know the proportion of metals to rocks and that it's similar to Earth, as is pictured here. We don't have any seismographs on the surface. We've landed on the surface many times. The US a couple times, mostly the Soviets did it. And as I mentioned before, those probes melt because the surface is incredibly hot. So we haven't been able to deposit long-term seismographic equipment on the surface, or any seismographic equipment. So we can't use Venus quakes to probe the interior, but a reasonable assumption is it's probably pretty much the same as Earth. Same mass, same size, same density, same composition. The interior probably looks a lot like ours. There will be one difference, though. The similarity is that, well, if it's the same interior, that means Venus's outer core is liquid molten iron, a conductive fluid. And on Earth, our rotation causes these eddy currents and generates our global magnetic field. Will Venus have a strong magnetic field? Let's say it does have a conductive fluid layer. Will it have a strong magnetic field? Yes or no? I'm getting some.
No. No.
Yep. Again, the head's going this way, but better to have a vocal response because then I can ask why.
Because its rotation is so slow?
because its rotation is so slow. We get these eddy currents on Earth because we're spinning quickly. 1 day or faster is considered rapid. 1 month or slower is considered slow. So Venus is not churning up that conductive fluid layer. And so we don't expect a magnetic field. And indeed, we don't detect one. There's no magnetic field there. Okay, that's pretty much all we can say about the interior. So let's move on to the surface. Here are some pictures of the surface. Again, we have landed, or mostly the Soviets. This is a Soviet lander, Venera 13. And it lands, and it can take a few pictures before it melts. And it's not like the whole thing melts. I mean, it's hot. And they measured the temperature on the surface. It's 730 degrees Kelvin, which corresponds to 855 Fahrenheit. So it's hot, and the metal will get soft. It's not going to like turn into a puddle on the ground, but it will melt the electronics and it will cease functioning after about an hour. But we've got a few pictures just of the immediate surface around the lander. The top is the true color. It's very yellow just because the atmosphere, the stuff that's in it, and it being so thick, it blocks a lot of the blue light. But they included a color correction bar, red, white, and blue, which is our colors, but yeah, it's also the Russian colors, I guess, but not the Soviet colors. Anyway, they used it to color correct it to show you what it would look like under Earth illumination. And that's the bottom panel, and it doesn't look very dissimilar from many barren, rocky places here on Earth. But the difference is, it's really hot. And so even though it looks rocky and you could stand on it and not notice anything, on geological timescales, it's going to move differently on Venus than on Earth. Come back to that in a second. If we want a better idea of the whole surface, we have to use radar techniques. We have to send a spacecraft there, put it in orbit, and use radar to penetrate the clouds. And we first did this in the 70s. This is the Pioneer Venus Orbiter, or at least an artist rendering of it. It's actually the first experiment that I cut my teeth on as a young scientist. I wasn't studying Venus, but on board that spacecraft and on board many spacecraft in the solar system, they attach small gamma ray detectors to study gamma ray bursts. And by spreading them throughout the solar system, we could figure out where they're coming from because timing, it hits one detector first, then another, then another. Through the timing, we could figure out where they were coming from. So that's some of the early work I was doing when I was a student. Anyway, Pioneer Venus Orbiter used radar, so it sends radar down through the clouds and it times it. If it comes back a little bit sooner, they know they just hit a mountaintop. If it comes back with a delay, then it had to go down into a valley and come back through that valley. So that would slow it down. I mean, we're talking minuscule fractions of a second, but we can measure that. And so we can measure elevations. And this is an elevation map of most of Venus from about -65 up to +75 degrees. The orbit didn't permit it to map the poles. And we have regions of different elevation. Now, don't be confused by the color. Blue does not mean water and white does not mean snow. As we'll see, there's no water on Venus in any form. You'll see that when we talk about the atmosphere. But this is just how they colored the different elevations to kind of match it to elevations on Earth. So you have low regions and you have higher up regions. The higher up regions are called terra, and sometimes they're called continents. But take that in quotes. They're not continents like here on Earth. On Earth, the continents are riding on plates and the plates are moving around. We don't have plate tectonics on Venus. The crust is moving, but in a different fashion, as we'll see. Also, the names Ishtar and Aphrodite, everything on Venus, almost everything is named after women. It's just the naming convention. I think an early mountain was named after Maxwell, who's male, a male scientist. So I think of Maxwell. He's the only man on a planet full of women, so not a bad deal for him. Anyway, I'll have to cut that out of the video for PC reasons, I guess. I don't know. Anyway, here's the comparable image of Earth, the elevation map. Again, blue does not mean water. White does not mean snow, though it does kind of work out that way, given how they've drawn the colors on the Earth map. And if you look at the Earth map, they're showing the ocean. They've taken out the water, and you can see the elevations down in the ocean floor, and you can see where the plates come together. You can see the Mid-Atlantic Trench very nicely, and in other locations as well, you can see the boundaries of the plates. And particularly if we had a better image and zoomed in and studied it carefully, you can pick them out in the elevation maps. But you look over at Venus and you don't see any such boundaries. So there are no plates on Venus. It doesn't mean the surface isn't moving, it's just moving in a very different kind of way. So to figure out the difference, let's compare Earth to Venus. This is just a review of Earth. We have a convecting mantle. On top of it, we have a solid crust. And it's because the temperature is cold. It's cold enough for it to be in a solid form. So the mantle carries the plates and they run into each other. Sometimes you have subduction zones, and then inland you have subduction volcanoes. The difference on Venus is it's just so damn hot on the surface that even the surface has this plasticky nature. Again, it's not plastic, but we use the term to mean slowly flowing. You could stand on it, it will feel solid to you, but over geological timescales, it flows kind of like a liquid. And so you have the convecting mantle, and instead of plates flowing over it, it just kind of pushes through. If you have one of these regions it's convecting upwards, it pushes through, making what we call a shield volcano, not a subduction volcano that requires solid plates. This is a shield volcano where you poke through the surface. And we have these on Earth too. The Hawaiian island chain is a good example. They're in the middle of a plate. It's just a weak spot. The mantle's poked through and made an island. Then the plate carries the island away, and then it pokes up again in the same spot, making another island. So you get a chain of islands. We have shield volcanoes in various places on Earth too. In Venus, it's all shield volcanoes. Wherever the mantle is poking up, it pokes up through the soft surface, creating a volcano, and it dumps out lava and magma, and then it pushes radially around these shield volcanoes. That's how the surface moves on Venus. It's pushed radially from these points, and then you have regions where the spreading surface runs into each other. Here we have a shield volcano. Imagine a shield volcano over here. They're both spreading, and so there'd be a region between them where the material runs into each other, and you get both pileups and downwellings. It kind of crunches, some of it up, some of it down. The stuff that's crunched down can get pulled back down by the lowering part of the convective cycle. So the surface works very differently. The surface moves, just not through plate tectonics. So just to illustrate that, these are pictures I made myself with Microsoft Paint. Here on Earth, solid plates moving in different directions, running into each other. On Venus, you have the radial spreading, and your compression zone would be right here. Okay, well, that's the idea. That's what should happen according to the geologists, but you can't see it in the PVO data. We need much better resolution, much better technology to do that. And so a couple of decades later, in the 90s, NASA sent Magellan. Here it is being launched from the Space Shuttle cargo bay, went into Venus orbit, mapped the surface in exquisite detail, and this is what we have here. Again, it didn't do great with the polar regions, just given how its orbit was designed, but tremendous detail everywhere else. And it got not just elevation information, but reflectivity. Different types of rocks will reflect radio waves differently. And so the lighter colored, that's going to be like a basaltic rock, the kind of stuff that came up on the moon after the moon was hit, the interior leaking out. And I don't know if it's lighter in reality. On the moon, it's darker. But here in these radar maps, it comes out as lighter than the other material. And so we can reconstruct pictures as if we were standing there on one of the volcanoes, because all it is elevation data. For each point, we know how high it is and what color to color it, its reflectivity. No one ever stood here. The spacecraft was never in this low of an orbit, but in a computer, we can reconstruct what the view would look like. And this is a typical view. Everywhere on the surface is covered in volcanoes, everywhere you look. And here's some of them here. And again, you can see the flow. That's the lighter color in these reconstructions. Here's the same idea. This is a top-down picture. They didn't color this one, but the lighter is the more reflective lava-like material. You can see it flowing from Thea Mons. Mons means mountain or volcano in this case. We see things that look like riverbeds, but no water ever flowed here. It was always too hot. So this was carved out by the lava, and it left it empty in this case. They're called channels. Here you see a compression zone. You see some material going this way and some going that way. And here's the compression zone it's halfway between two shield volcanoes. So it is as the geologist expected. It's kind of sloshing its way across the surface. And then we found some structures that we don't find on Earth. They're kind of unique to Venus. These are called lava domes, and they're wannabe volcanoes. They're regions where the material is trying to poke up through, but it can't accumulate. It keeps falling back down into the ground around it. Here's again a reconstruction, an elevation reconstruction. It's poking up, but then pouring right back down on the sides. And they only last as long as you have enough pressure underneath pushing the material up. But the convective patterns underneath are always changing. And so here's a region where the pressure has dissipated. The convective cycle underneath moved to some other place. And so here's a lava dome that collapsed. You still have some active lava domes in the outskirts, but this one collapsed and the whole region sunk. And when you do that, you get coronae, that's the plural, and not like the virus, but or the beer, but these circular patterns. And it just, as it came down, it kind of fractured in that way. And then you get what they call fractures, which emanate from there in a very different looking kind of crack in the ground. That basically the ground sunk, and then you develop these different types of cracks, coronae and fractures. Here's another fracture. And again, it's not necessarily lighter in color, it's just more reflective. It could be a perfect color match for all we know if you were standing there looking at it, but showing you some of the underlying more reflective material. And occasionally a meteor will get through. It's a really thick atmosphere, so most incoming meteors, they burn up and don't hit the surface. But if you have a really big one, it will make it through. And from the scale here, you can see this is an impact crater that's like 100 kilometers across, so it's huge. I have a little animation here. It's not the highest quality. It's made back in the 90s, so it's pretty low resolution. And I'll play it with fast forward so we stay on time. But it's just a fly through this elevation data, like a flight simulator. There's that crater, lava flows. Just some astronomer / computer programmer having too much fun. So a quick fly through from over that area of Venus. And then lastly, we're going to talk about the atmosphere in the last 10 minutes and its evolution. So let's start with Earth's atmosphere. What we'll do is we'll consider Earth's atmosphere. Again, I'll just refresh your memory. And then we'll say, what happens if we take Earth and we move it to Venus's distance from the sun? What would happen? So on Earth, we have this cycle going on. We have volcanoes, and they spit out water vapor, carbon dioxide, and sulfur dioxide, and other things too. But let's focus on those three. Since Earth is farther from the sun and cooler, the water falls to the surface, rains, gives us oceans. And then once we have the oceans, as we learned before, the CO2 and the SO2 can dissolve in the oceans, forming the sedimentary rocks. And over long times, geological times, those rocks get carried along and they find themselves under volcanoes and they get outgassed again. It's a cycle. It's a healthy geological cycle that you see in geologically active planets like our own. Venus is a little different, but before we go to Venus, let me just sketch out on the dot cam what would happen if we took Earth and moved it closer. So talking about the atmosphere, if Earth was moved to 0.7 AU from the sun, that's where Venus is, of course, the temperature would go up. You've all used the temperature equation. You know how to calculate the temperature of a world given its distance from the sun. If you use that equation, you would learn the temperature would go up 50 degrees, just due to the greater proximity. But that's just the beginning of the story. It gets worse. But 50 degrees Kelvin, that would bring us up. We would become 150 degrees Fahrenheit, just to put that in context. Not really good for us. That's too hot for us. But it gets far worse. It would get far worse if we did this to the Earth. So what happens to the water? We know water boils at 212 degrees, so it's not like the oceans will boil off in this scenario. But what will the water do, at least more rapidly than it does now? Anyone want to guess?
It would rise.
It would rise, yeah. What's the scientific term for that? The water coming out of the oceans. It is
evaporating.
That's right. Yep, we evaporate. So the evaporation happens more quickly. So in this case, we end up with more H2O in the atmosphere. ATM, atmosphere. And that causes the temperature to rise because water is the most important greenhouse gas. We learned about that with Earth. So if we put more water in the atmosphere, the temperature goes up. The temperature goes up, we evaporate more quickly, which puts more water in the atmosphere, which causes the temperature to go up. So it's a cycle, it's a runaway cycle. We call this a runaway greenhouse effect. We do have a greenhouse effect here on Earth, and it's stable except for the man-made component that we're adding to it. But here, this would be a natural runaway. And you end up, in the end, with no oceans, all that water in the atmosphere, and as we'll see in a second, the carbon dioxide also in the atmosphere, because without oceans, it has no place to go. And so the temperature would, in this case, be about 1,500 Kelvin. So crazy hot. Now we know this is not the end of the story because Venus is only 730 Kelvin. So we have a few more things we need to track. But here's the slide for Venus. We have volcanoes. We have tons of volcanoes, and they're spewing up the same stuff: water vapor, carbon dioxide, and SO2, sulfur dioxide. But without the oceans, it's different. And I should be clear here. Venus never had oceans. What I just worked through on the doc cam was if we took Earth and slid it closer to the sun, our oceans would evaporate. Venus was always that close, so they never had oceans. It was too hot for it to liquefy and rain down. It always stayed in the atmosphere. So let's consider what happens to some of the stuff under that surface. It's written here, but I'm just going to describe it on the doc cam. So in this case, let's start with the carbon dioxide. There are no oceans. It can't dissolve into rocks, and so it stays in the atmosphere, and that is contributing to that 1,500 Kelvin temperature because carbon dioxide is also a greenhouse gas. And then the water vapor, two things happen to it. The first is H2O can combine with the SO2, which is also stuck in the atmosphere. No oceans, it has no place to go. It's in the atmosphere. And when it bumps into H2O with the right amount of energy, it forms H2SO4, which is sulfuric acid. And so on Venus, you have sulfuric acid clouds, sulfuric acid rain. On Earth, we have water clouds and water rain. There, it's sulfuric acid primarily. And there's a side effect. This sulfuric acid is highly reflective. Gives the planet an albedo of 0.75. Earth's albedo, Earth's reflectivity is 30%. Here, 75% gets reflected, and that's partially why it's so bright. The morning star, the evening star. It's bright because it's close to the sun, reflecting that light close to us, but also very, very reflective, almost like a mirror. Now, the second thing that happens to the water, there's no ozone layer to grab up the ultraviolet light from the sun. So these ultraviolet photons strike the water and break it into H2 and O. That H2 is lightweight, floats out into space. The O combines with other stuff. It's taken out of the atmosphere. So any water vapor that's in the atmosphere goes away, drops down to nothing, making Venus the driest place in the solar system. Even with Mercury, we saw there's water frozen in the polar cap, same with the moon. So there's water there, but on Venus, there's nothing. Through these two processes, it becomes incredibly arid. And you take out the water vapor, the temperature will drop because that's the most important greenhouse gas. It drops down to the 730 Kelvin that we mentioned before. And that's just caused from the CO2. And the atmosphere is primarily carbon dioxide, 90-some%. We had a warm-up question a few classes ago that had the exact percentage, but mostly carbon dioxide atmosphere, runaway greenhouse effect. So we'll just end with a couple slides here. So we looked at a slide like this for Earth. This is the counterpart for Venus. The temperature on the surface, that's this blue curve, the temperature goes all the way up to 730. The higher up you go, the cooler it gets. And it inverts up here around 100 kilometers. And so that defines the top of the troposphere. On Earth, the troposphere stops at 12 kilometers because then we have that temperature inversion caused by the ozone collecting heat from the sun. We don't have that here, so the troposphere goes all the way up to 100 kilometers, which on Earth, we consider that the boundary of space. So it's a thick atmosphere. Yeah, and so this is going to be your convective atmospheric region all throughout here. And as I said before, you have complete cloud cover, sulfuric acid clouds, sulfuric acid haze, and probably sulfuric acid rain. And lastly, let's just compare the greenhouse effect between the two worlds. Here's Earth. Visible light comes in, 30% is reflected from the clouds, from the polar caps. 70% makes it through, is absorbed, converted to infrared, most of which escapes. A little bit is held in by the water vapor, by the carbon dioxide. Small greenhouse effect here on Earth. Boosts our temperature 60 degrees. On Venus, most of the light is reflected. 75% is reflected. Only 25% makes it through. So that's a cooling effect. And it's absorbed and re-emitted as infrared, but given the extreme runaway greenhouse effect, almost all of that's trapped and only a little bit leaks out. And so it boosts the temperature tremendously. Despite less energy, a smaller fraction's getting in, a much, much greater fraction's being retained. Okay, so that's it for Venus, and we're out of time. We'll pick up with Mars next time after the exam. Thanks.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
The usual question.
Okay.
Can you go back to the notes? Number two.
Oh, okay, yeah. So which sheet would you like? This one, the previous?
That's good. This is good. This is good. Thank you.
Okay.
And then do you mind going back to how you solved the introduction question?
Yeah. So here's the question. And the solution is actually in the ebook notes written out, but I'll just put this version back up. So first key thing is the zircon crystal. That means we can treat all of these lead atoms as coming from uranium, because there's no other way to get lead into a zircon crystal other than it starting as uranium and decaying into it. And so one uranium atom for every 64 lead atoms means now we have one, and in the past we had 1 plus 63 equals 64.
Okay, thank you. And then can you just like move the piece of paper so I can?
Yep, there you go.
Yeah. So what does that say? 6 years next to 0.713
Oh, six
right there.
times, 6 times. So 1/64 corresponds to 1/2 multiplied 6 times. That means we've been through 6 half-lives. So 6 times the half-life of this decay, gigayears. Oh, I see what you're asking. That's a G. Gigayears.
A giga year?
A gigayear. That's a billion
All
years.
right. A billion years.
Yep. I thought you were talking about this 6. Sorry.
Okay, thank you. Have a good one.
Professor, I had a quick question. It was about just real quick. It was about Venus and like why is it day for or night for like those extreme amount of times? Is that because I can kind of see that it's from like the lower like rotation speed, but like why is the rotation speed lower? Is what I'm trying to ask.
Yeah, so why is the rotation speed lower? We don't know for sure. There are 3 possible explanations. One is something struck it and nulled out its rotation. Like if you're spinning a bicycle wheel and then you slam it against its spin direction, it can stop. Another possibility is the friction with the atmosphere slowed down the planet from rotating. So the atmosphere is going around at a high speed and there's some friction with the ground, and it doesn't seem like it would, but after 4.5 billion years, it technically can. And the third possibility is Venus might have been closer to the sun in the past and got tidally locked and then moved farther away and lost a little bit of that tidal locking. But if it was closer, that could have slowed its rotation to match its orbiting speed.
Okay, that makes sense. Thank you. You have a good one.
You too.